In the last lecture, we were considering the various characteristics and implications of the properties of the system function HFS, which is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input with the zero initial conditions in the system. When we say zero initial conditions in the system, we don't really end up with any loss of generality, because any initial condition in the system can be replaced by an equivalent source, as we have thought of in the case of electrical networks, and similarly in the case of systems as additional inputs. We can think of non-zero initial conditions as additional inputs, and therefore each non-zero initial condition can be thought of as a separate excitation, and one can use the superposition principle. Therefore, when we say zero initial conditions, there is really no loss of generality. We considered various aspects of the characteristics of HFS. Now let us start with consider once again the free response of the system as given by the poles of HFS. We said in the last lecture that as far as the output is concerned, it consists of two parts, one which corresponds to the poles of XFS and one which consists of the poles of HFS. The poles of XFS give rise to the forced response part of the output, and the poles of HFS will give the part corresponding to the free response of the system or the natural response of the system. And the poles of HFS are indeed the zeros of FFS, which is the denominator of the polynomial in the denominator polynomial in HFS. Now, depending on the location of the poles of HFS, we have different types of behavior. So in the complex plane, if this is the complex plane, S plane, suppose I have a pole here at the location A, then that corresponds to, in the partial fraction expansion, k over S plus, this is minus A, let us say, k over S plus A, and this will give rise to a response k e to the power of minus at. So that is something which decays with time. On the other hand, if I have a pair of complex conjugate poles here, say at locations B, say this is A, at the location B, this will be Ks plus say m divided by S plus alpha whole squared plus omega naught squared. That will be the type of expansion, the partial fraction expansion that you get corresponding to the locations in the B positions, where this is minus alpha and this is omega naught. And that gives rise to a response which is some, say, a e to the power of minus alpha t sine omega t plus beta, which means that you are having a decaying oscillations with the amplitude decaying exponentially. On the other hand, if you are having a pair of poles on the imaginary axis, location C, that corresponds to something like Ks plus m once again over S squared plus omega naught squared, and this gives rise to a response which is sine omega naught t plus beta, which is sustained oscillations. Therefore, the poles of HFS dictate the natural response of the system. On the other hand, if there is a pole in the right half plane, suppose there is a pole here, that corresponds to, suppose this is D, S minus D, then this corresponds to k e to the power of dt, and that is represents an increasing exponential which indicates instability. So one can say that if the system is stable, if you have a bounded input giving to raised to an XFS which is finite, then the natural response must decay with time, or at least stay steady with time. It should not take off, it cannot go indefinitely to large quantities. Therefore, for stable system we require all the poles of HFS to be in the left half plane, and as a borderline they can be on the imaginary axis, because that is the limiting behavior. However, what happens if the poles are repeated? Repeated poles really mean that in the denominator polynomial HFS, you have factors like S plus alpha whole squared or S squared plus omega naught squared whole squared or s plus alpha square plus omega naught square whole squared if the repetition is of the order 2. So let us consider what happens if you in the complex plane you have a pole of order 2 here, that means multiplicity 2, a repeated pole. It can be repeated 2 times, 3 times and so on, but let us illustrate it for the case of 2. That means in the partial fraction expansion here you have k over s plus alpha whole squared, and the time domain response corresponding to this will be at the form kt e to the power of minus alpha t. So that means you have it exponentially decays but starts with 0 amplitude. On the other hand, if you are having 2 complex conjugate poles repeated like this, that will be of the form some f of s over s plus alpha whole squared plus omega naught squared whole squared. That means these 2 complex conjugate poles are repeated twice, and this gives rise to a response which will be once again this envelope, it will be like this. So even though the poles are repeated they are in the left half plane, it gives rise to a stable response. The response ultimately decays. What happens if there are repeated poles on the imaginary axis? Suppose there are order 2. So this corresponds to a term like f of s over s squared plus omega naught squared whole squared, and this gives rise to a time response which is some kt sine omega t plus theta. That means the time response corresponding to that would be something like this. So this certainly should be excluded if we want a stable system, if we have a reasonably well behaved bounded type of input. The output cannot grow indefinitely large for a stable system. So that means we cannot have repeated poles on the imaginary axis. Certainly we cannot have poles in the right half plane, whether it is repeated or simple, and on the imaginary axis we cannot have repeated poles. Even repetition of by an order a duplication of poles, that is multiple rows order 2 themselves are not permitted. Certainly higher order poles cannot be permitted. But as far as the left half plane is concerned, what we have illustrated for order 2 can also be extended for higher order. That means you can have a pole on the negative real axis of order 4, 5, 6, whatever it might be, and similarly complex conjugate poles in the interior of the left half plane can be of any order whatsoever. Ultimately the response will decay. On the imaginary axis, however, you can have only simple poles. That means to conclude this discussion, if we want to have the free response to decay with time, then we require that the poles of h of s should be in the left half plane, in the interior of the left half plane. If they are on the imaginary axis, they must be simple. They must be of unit multiplicity, they cannot be repeated. And certainly we cannot permit poles of any order in the right half plane. So that is the meaning of the stability. So if the system is stable, a bounded input must give rise to a bounded response, and so the response cannot go on, cannot take off to infinite limits. It can't grow indefinitely with reference to time, and the requirement therefore is that the poles should be in the left half plane. If on the imaginary axis, they should be simple. Let us now look in some detail the forced response characteristics of the system. We know that y of s equals h of s times x of s. Now we will take a particular case of x of s, which is of the form xt is a e to the power of, say, s naught t. That is an exponential signal. Then it gives rise to a forced response y of t, which we have already seen in our preliminary lectures. Y of t will be h of s naught times a e to the power of s naught t, which means this is h of s naught times e to the x of t. So whenever x of t is of an exponential type, exponential signal with a complex frequency s naught, the forced response is obtained merely by multiplying x of t by h of s evaluated at that complex frequency. Hs, s, you substitute s naught for s, and that is what you get. This is something which we already discussed. Let us see how it arises. We know that if xt is a to the power of s naught t, y of s will be h of s times the Laplace transform of x of t is a divided by s minus s naught. So in the partial fraction expansion of this, you have one term corresponding to S minus S naught, which is H of S naught times A, plus terms corresponding to poles of H of S. So there are other terms which correspond to poles of S. They give rise to the free response. The forced response is given by this. This gives you the forced response. And so from this, y of t, the time domain representation of this is A times H of S naught times e to the power of S naught t. So that is what we are having. That's exactly what we said is the forced response. So this is how it ties up with the Laplace transform theory. What we already know from your preliminary lectures, whenever an exponential signal is there, the output, the forced response is the input times H of S naught. Now, arising out of this, we can talk about the frequency response characteristics. Suppose you have e to the power of j omega naught t as the input quantity. Then we know the forced response of this. The forced response of the system, y(f) of t, this is x of t. The forced response is h of j omega naught e to the power of j omega naught. So this is the frequency response function. But we are often interested not in exponential signals of the set e to the power of j omega naught t, but something like cos omega naught t, let us say. So cos omega naught t, we can take this as a real part of e to the power of j omega naught t, and therefore the response to that would be the real part of h of j omega naught times e to the power of j omega naught t. So this can be written as, if h of j omega naught as a magnitude h of j omega naught, so h of j omega naught magnitude times some phase. So the magnitude of this is h of j omega naught cos omega naught t plus an angle which is the angle of h of j omega naught t. So that will be what you are having. So depending upon, if cos omega naught t is the input quantity, the output quantity is given by the magnitude, is magnified by the magnitude of the frequency response function. The phase is increased by the the angle of the frequency response function, cos omega naught t plus angle of h of j omega naught t. Similarly, if you have sin omega naught t, the forced response will be h of j omega naught sin omega naught t plus the angle of h of j omega naught. So this is the frequency response function. We have talked about this when we discussed the Fourier transform and Fourier series, Fourier methods, and there h of s substitution s equal to j omega will give the frequency response function. So we can see how this ties up with our Laplace transformation theory. To summarize then, what we have talked about is the total response with 0 initial conditions. If the input is delta t, it gives rise to h of t. And the Laplace transform of that is h of s. The Laplace transform of the output is h of s. If the input is ut, I'm sorry, not this, it's only the arrow, this is the input, this is the output. We call that the initial response or step response at, and we indicated this as as. That will be h of s over s. So we have a general xt. Then in terms of The impulse response we say is xt convolved with ht, which in Laplace transform domain is xs times hs. We can also have alternately x dash t convolved with at. The convolved with at, that is the step response. The meaning of this is x0 plus at plus 0 plus 2t of x dash t x dash tau at minus tau d tau. All this we discussed in the last lecture. So in terms of Laplace transforms, we can write x of s times s. We also have an alternative representation of this. If you recall, you can write this as a dash t convolved with x of t. That also has the same Laplace transform. And in these two expressions, a dash t and x dash t, we are talking about the situation we take t starting from 0 minus, starting from t greater than or 0 minus. So that is what the total response of a system can be obtained from the either the step response or the impulse response, or in general terms, this is how these equations will run. Now let us talk about set up a similar table for the forced response. So if the input is an exponential signal a e to the power of s naught t, the forced response is h s naught times e to the power of s naught t. If it is e to the power of j omega naught t, it is h j omega naught e to the power of j omega naught t. And if it is cos omega naught t, it is h j omega naught magnitude cos omega naught t plus the argument of h of j omega naught. So h of j omega naught is a complex number, and whatever angle that it has got, that is the addition to the phase of the cosine function. Sin omega naught t, this will be likewise h j omega naught magnitude sin omega naught t plus the argument of h of j omega naught. And h of j omega is called the frequency response function. Which we had used in steady state sinusoidal analysis, circuit analysis. After all, h of j omega is something like your impedance z, y, and all related to h of j omega. Z is a function of omega, h of j omega is a function of omega. So impedance is the ratio of voltage to current. So if you take the voltage, the response quantity, and the current as the input quantity, the system function corresponding to that is z in the normally what we talk about z is a system function in this context. Let us now work out an example to illustrate these ideas.